So, Peter has already kind of described what was happening. We met at HEP workshop. Then I looked at this paper, which is the roadmap for HEP, because I anticipated that you guys kind of sketch your problems. And that this paper, this community paper, which is currently on the screen, was our starting point. And then we reached out to Peter to kind of we gave him some of our initial understanding of what we want to build, and he came up with those examples which he mentioned. And so the plan for today is kind of like go through these examples and explain how we see solving them. That in our understanding will be obviously incomplete because we just see that from one side, but you guys see it from the other side, but maybe we'll be able to converge. So just to start with a concrete thing, so we look at this first example, which is exploratory data analysis from this paper by Peter and Jim and other people. So idea here is that Peter and Jim said that, okay, we have this reasonably large data set, 5.4 million events. I mean, it looks a little bit smallish to us, but Peter says, okay, maybe 10 of those are participating in every exploratory analysis, and people run queries against those data sets. Some simple queries like mentioned in that paper. So, for example, they are choosing an element with a maximum p tau, or computing the mass of pairs. Like essentially, it's like you probably know it better, but it's like you add each mass of each element with each other element. And I don't know if you can see my pointer here. So it's like this. It's two nested loop. It's two loops. One is nested, and then you compute the mass according to this formula. So it's a floating point computation. If we understand correctly, normally muons are single point precision. Mass is double, and you run over like the entire data set. And the question is like, can we make it faster? And the idea which we have in general, like for approaching those kind of workloads, is to use programmable hardware, which is FPGA. So let me just explain what it is. So I don't know, maybe some of you guys know, but the idea is that field programmable gate arrays are like specifically designed circuits which can be reconfigured or programmed after deployment. So it looks like a chip, but internally, it's some of it is a programmable interconnect, which connects logic elements and connects some I/O blocks. And essentially, if you use a language, and it used to be that the languages were really low level, but today you can use something like a C-like OpenCL language. And essentially, the compiler toolchain can take it into some intermediate representation, then do hardware synthesis, essentially route proper logic, and this FPGA will essentially just be designed to solve a specific function. So like in hardware, so it will be adding floating point numbers, will be like doing some logic on integer elements, right? And the way it looks today in practice is that this is like Intel Stratix 10 FPGA. It's the top-of-the-line FPGA, which is like the chip itself deployed as a PCIe card, which has some memory on board here. So it has 8 GB of DRAM. It has network connections, like 4 network ports, which allow you to bypass the other network adapters and connect to other FPGAs or to other machines in the network. And it's reasonably powerful. So later on we will like give a short comparison versus GPUs. But so this PCIe attached FPGAs, they can connect to host memory. We are PCIe DMA, direct memory access engine. So essentially the FPGA can read and write host memory, but it looks like that you have to issue a write and of a block of memory and then read it, right? The second flavor of FPGAs, which is also deployed right now, are sitting on the cache coherent memory bus. So here is another example from Intel, which is called HARP, and FPGA here, which is again similar chip, slightly less powerful, but again we can expect that they become all about like they will be equally powerful like the next year or two. Is sitting on a cache coherence bus, and then it can access any byte from the host memory. So essentially, FPGA can issue a memory read and get a cache line. So it simplifies programming a lot because you don't have to do anything with your data structures. So if you pass like a pointer to the root of a tree, for example, you can walk it in FPGA in a very similar manner how you would walk it on a regular CPU. Okay, so we have this hardware, right? So it's coming. And the idea is that now, how can we solve this original problem which we have here? So, for example, max p-tau or mass of pairs, right? So what we're thinking of is start designing inside FPGA, this custom programmable pipelines, essentially this side on the right, like on a slide that's on the right, which essentially connects to the host program here. So for example, if you had like a mass function, so instead of really using the main CPU to compute the mass, essentially going through finding adding all elements of your data set with each other, we send a message to the FPGA, and depending on whether it's cache coherent or it's accesses host memory via PCIe, there is not that much difference for us, but it provides a slightly higher latency of access. We send a message to FPGA, then we implement our custom prefetch unit. I will talk about it a little bit later, which essentially makes sure that the data is available for FPGA. But the idea is that we implement the logic of these functions, max here and mass of pairs, as FPGA logic. And because FPGA they have a capacity to implement the same function multiple times. So for example, FPGA can probably do up to like 5,000 of floating point operations per cycle. We can use techniques like dataset partitioning to process the set in parallel, and then just find individual maximus and maximums, and then like find a single one, or do the masses in parallel as well. So like through some kind of a loop unrolling. And essentially then we reply back to the host saying, okay, here's the answer, right? So this high-level intuition is clear. Are there any questions about it?
Yes, there is. This is Jim.
Hi, Jim.
I wrote that you're getting the functions from.
Yeah.
While this sounds like a great technique for some applications, the application I was describing in that paper might not be the right one, because this, first of all, those query functions, that's not actually how we do things yet.
Mm-hmm.
We usually write large, heavy-handed applications that take a long time to run. With the goal of that paper was to get into a more agile situation where physicists will be able to write these functions in a matter of several seconds, and then run them in a matter of several seconds, get a response, and then write a different function for several seconds. In order to get a more interactive, snappy feedback in doing data analysis. Putting functions on FPGAs can make them very fast, but I know that the assembly process can be hours sometimes. It doesn't seem like the right application for this.
It's yes and no, depending on how like diverse your function set is. So the idea is that you have a set of pre-computed, pre-synthesized logic for each function. So for example, for a max of pairs, for just a max, for something. And then you can plug into your interpreter, like this interactive interpreter, which you want to use, and compose these functions into something more complicated, right? So, and FPGAs today, like it's actually here on the slide, they support partial reconfiguration. So essentially, you can first of all like reconfigure half of the FPGA logic, or quickly replace one implementation with another. So we might have FPGA split into some subset of functions which are like hot today, and execute like specifically those functions on FPGA.
Yeah.
And I agree with you that like hitting the right workload is hard, and that's essentially part of the meeting is to figure it out.
Mm-hmm.
Let me move on a little bit, because there is much more to this basic figure which I'm showing right now, and then by the end maybe you and I get your point. So let's talk more about it.
But let me just ask a quick question. What it sounds like, Jim, is that you're saying that in the interactive scenario, people can come up with an arbitrary function, basically, right?
Yes.
And
yes. My list
back.
is very diverse. Very, very diverse.
Okay.
We should then like figure out how long the synthesis is taking for those simple functions.
It takes a while, regardless of the function. It's just the way because this is a large array. To synthesize something for the entire array takes 2-3 hours.
Mm-hmm.
If it's a small piece, it could be faster.
And Jim, you're saying that people do not reuse those simple functions at all?
Well, not these. These were just examples, and one thing that's kind of hard to convey in a paper is that
complex, the real.
Yeah, it's like whether you mean these or you mean things like this, and it was really just these are the this is sort of the beginning of the complexity of it. It would be very interesting and very domain specific for us to try to figure out if what we do with all of the procedural code that we write today could be sort of atomized into declarative pieces that could be put together, where each of these declarative pieces is a FPGA kernel and is super fast, and then some language pieces them together. It would be interesting to see if our work could be described that way, but it would involve a lot of working with people doing actual analyses to make sure that our set of kernels is broad enough and combinational enough that they could actually build their analyses from pieces instead of writing their analyses as arbitrary functions as they do now.
Yeah, we actually worked for the last year and a half on something similar for graphics. So the graphics guys defined 60 primitives. They're not trivial, but the real stuff is built from those. So if something like that can be done, that would be great. Yeah.
Yeah, it would be great. It would be like a revolution in our field to be able to express what we do in 60 primitives.
Yeah, so we should probably take a look at the code, and like that's probably the next step, just to try to understand whether it's doable on FPGAs. And I mean, anything is probably doable. The question is like whether it is getting faster or not. But okay, let me keep moving because the one other thing.
One more question. So Jim, you kind of alluded that there are other, well, I don't want to call them workloads, but like when you run not analysis but complete programs. Did I understand that correctly? That there are other cases that you may want to, let's call it, accelerate?
Other cases?
There are other computational examples outside of the analysis, such as the tracking problem that I sent you. The simulation, right?
Yeah, so we mentioned them. We talk about them later a little bit, although we don't understand them yet.
Okay, so then let's move on then.
Yeah. Like the very first question which people normally have is that how does this compare to GPUs? Because people know that de facto standard in acceleration is NVIDIA GPUs, and so here is a short comparison of the top of the line NVIDIA Tesla V100 GPU versus this Intel Stratix FPGA. So NVIDIA can achieve theoretical 15 teraflops single point operation throughput. This Intel Stratix FPGA can do 10 teraflops. So it's in terms of performance, it gets like very close. So it's like two-thirds of the speed. But at the same time, in terms of power efficiency, FPGAs beat GPUs even today. So essentially, NVIDIA can do 60 gigaflops per watt, and FPGA can do 80 gigaflops per watt. But the other thing which FPGAs give us is FPGA give us more control. So essentially, we can program really tricky cases and control the entire data plane, essentially, and that's what I will be talking about right now in the subsequent slides. That's essentially the ability to connect to the network, connect to the storage devices, and like program really simple kind of like device drivers which run on FPGA and allow us to bypass CPU altogether in many cases. So essentially that's my slide which explains the same point. Following example. So again, we looked at this click integration, essentially this interactive interpreter which Jim just mentioned, and other, like, let's assume you use some other languages in which you want to plug some functions which are accelerated. And we assume, yes, we assume that this implementation of the function is available. However, the problem is following. So when you invoke a function like computer math on FPGA, it's no longer a function invocation. Instead, you have to send a message over some kind of a bus, either PCIe or shared memory. And even in shared memory, it takes around 355 nanoseconds to reach FPGA over QPI bus. And so obviously, instead of waiting for the result, it makes sense to move on with the program. And so we developed this custom lightweight asynchronous runtime, which allow us to block essentially like wrap a piece of code inside an async primitive. It works in burst C, so that's why we can essentially plug it in any other language, be it like an interpreted language, because it becomes a part of the runtime, or in the languages which natively support async, something like C++. We can use their mechanisms like futures. But essentially, the goal here is that you can, if you have a loop and you have multiple requests pending, or your program can be expressed as multiple asynchronous computation, you can invoke them asynchronously without waiting for each of them to complete at the same time. And so this, we believe, allows an easy integration with existing software stacks. So essentially, if you have something written in C, you just say, okay, async, and it transparently invokes FPGA underneath, but at the same time, you don't have to wait for the entire function to complete. Obviously, the function itself takes some time on FPGA as well. So and the entire change which you have to do in a program often is simply just add this async primitive and a couple of do-finish primitives to make sure that, okay, you wait for the results correctly. So that what give us hope that we can actually integrate with existing software like the one which you guys have, this Kalman filters, curve fitting, and Monte Carlo simulation. Further, the next problem which we have, and this is what FPGAs allow us to solve, is that obviously we need the data to be available for computation. And by virtue of being able to program FPGA, we can implement these custom prefetch engines. So FPGA itself has a small amount, 6 megabyte of block RAM. So this is something what is accessible within 1 or 2 cycles. It's on board. And then it has DRAM itself on the card. So for example, 6 or 4 gigabytes of RAM. And then we can also prefetch data from the host CPU memory. And essentially with that in mind, and you mentioned that you have this root format, which we don't understand exactly, but maybe there is a chance to essentially, like you say, use some kind of a column representation and essentially be able to scan, if it's simple enough, we can implement it in FPGA. And essentially simple means that anything you can write in C, you can write in FPGA as well. But if it allows the sequential access, we can stream through the host memory, essentially prefetch data for computation on FPGA, and make sure that it's available right when we're ready to compute. The next thing we wanted to do is essentially do the same trick, but for flash devices attached on a PCIe bus. So non-volatile memory on a PCIe bus, NVMe, essentially is like today's standard for fast non-volatile storage. And NVMe is a reasonably simple protocol. It's just a couple of producer-consumer ring buffers, so it's easy to do on FPGA as well. And we can prefetch directly from PCIe, essentially, from NVMe attached flash devices. And as faster memories will become available, and today we have the first prototypes of these non-volatile 3DX point devices, which are called Apache PAS, which are sitting on the memory bus, we can again prefetch from those memories as well. And again, the freedom is coming from the flexibility of programming in FPGA. And obviously, the next logical step, and this is how we're moving towards like this data center scale, is saying that, okay, not each machine will have an FPGA, but instead you can really use a low latency network to send requests over the network to FPGA units. So essentially, again, today, InfiniBand allows you 1 microsecond network access to another machine in a data center. But again, the early prototypes from Intel, which is called OmniPass, actually provides something like 600 nanosecond round trip. Because the network adapter is integrated on die with the CPU, so you can directly send network packets through, like, without going through PCIe. And again, like on the host CPU, this the same mass function, instead of like sending a message to an FPGA, it sends a message to this network adapter or one of these user-level device drivers which are available today, and it reaches FPGA on the network. FPGA receives the request, and like depending on where the data is, essentially fetches the data and does the computation for you. But the moment we can integrate with existing applications, this next step is kind of is not that hard. So like making them accessible over the network is doable. And obviously the logical step is that you can leverage the fact that you can send computation where somewhere where the data is stored. So essentially, if you can collocate computation and data, you can benefit from not having to move the data around to FPGAs. But essentially, if here we have a machine which has an FPGA board collocated with a storage board, we can essentially send computation there. And again, it's kind of becoming a standard technique in modern data centers. And it depends on the shape of your computation. Sometimes it makes sense to move the computation to data. Sometimes it makes sense to move data to computation because it's easier to synchronize. And we have to look at specific workloads and maybe like run some early benchmarks to understand what is better. But essentially, where we're moving is this kind of a general view of a data center in which you have pools of compute nodes which are equipped with FPGAs or some other accelerators, and we actually do not rule out the possibility of other accelerators, because if you're doing some kind of a machine learning workload, which probably is beyond the scope of this work, but then you might end up using like a dedicated CPUs which are designed specifically for machine learning, and we have a couple of those available today. Like it's Google TPU, Tensor Processing Unit, and the newest Intel chip, which is designed for spiking neural networks. And the same with storage. But the fact that we can connect FPGA natively on the network and essentially send network packets and like do not introduce additional latency by going through the host, or even if we go through the host, we use a very dedicated low latency network stack, allows us to use the entire to view the entire data center as a single system in which we can like quickly ship computation or data around. And at this point, you can say, okay, well, my workload is something like even like my particle or like trajectory fitting is expressible as a distributed computation. your choice of a language can be different because you might use something like existing primitive, and as long as you can offload it into that data center, or you can like say, well, like you say, I want a declarative language which will figure out what to do. And people do that with machine learning workloads because these TensorFlows are essentially like declarative languages, which then schedule computation on individual compute units available for this specific computation. Is probably like it's becoming feasible, but essentially the first part we build this primitives which allow us to build this pools of machines, compute, storage, and control plane, which runs on regular CPUs. And then the second part is designing those computations for this kind of environment. And so what we did like a couple of weeks ago, as Peter said, we looked at this couple of computations which are supposedly the most computationally intensive for HEP, high energy physics workloads, and one of these, obviously, this parallel particle trajectory fitting, and maybe it's a good candidate for this distributed programmable data center. Most likely it is, because the FPGAs are really efficient in implementing something like that. We also looked at like Peter said, at these Monte Carlo simulations with this GINT 4 toolkit. Again, we did not really understood them because, I mean, it's slightly beyond our like 1 hour of reading, but we are willing to put time and essentially just take a look at those workloads and maybe take a look at code and say, okay, can we essentially start writing, accelerating parts of these computations? Essentially what, again, like integrating with Clink is like we already discussed it, it's again possible. But what we want from you guys is essentially discussion of the data set sizes, like what is usually involved in a specific computation, how much memory, what are the access patterns, because even in that paper which we discussed in the beginning of this meeting, like 5 million events seems a little bit low, so because it's only like 400 megabytes of DRAM if it's a double point precision, right? And again, the same for Monte Carlo, the same for Kalman filter. So probably at this time, you guys would like start asking questions and like tell us where we are wrong and what you think can be done
or not.
Or not.
I have lots of things to say.
Yeah, go ahead.
Probably the best place to start would be on some fixed computations, such as the tracking problem, because that is something that is determined once, and you have to do it for many events. It would be wonderful if we could reduce our analysis problem to 60 primitives, and we actually, in our field, we should think about ways of trying to do that. But that's further afield. We're not really ready to be able to give you such a set of primitives. So something like the tracking problem, something where the problem is fixed. You mentioned the root file format.
Right.
We could have some very productive conversations about how to read root directly in FPGAs. I think that could be possible.
Yeah, and I mean, but the idea is that really to be successful here, you have to have a well-defined format which is designed for this distributed shared memory environment, and this is where everyone is moving today in other domains like genomics, any big data analytical processing. So you really carefully design your primitives to be able to quickly move data to compute units, and there is nothing contradictory about it. So you can say, well, I store my data in root in like long-term storage, but then you have to design a pipeline which essentially can pipe the data into faster non-volatile storage for processing. And as you say, like for example, if you do graph analytics, you just all of it bottlenecks on memory accesses. So you have to be very careful about how you design your in-memory data structures to stream to these graphs in a predictable manner, because the computation there is often like an integer increment. Here we have a couple of floating point additions, but like plotting datacenters also massively parallel. So most likely you can bottleneck on memory for many of those workloads. I mean, not for Kalman filter, I believe, but for something like this exploratory workloads. But I believe this is unavoidable for you guys one way or another. So you have to start thinking early, and it would be nice to if we can find it together. Then it will help us with this project and you with in the future as well.
Okay, so I didn't understand from that. Are you interested in building workloads that read from root sources directly, or are you suggesting that we should have an intermediate format for workloads that run on FPGAs?
I mean, first of all, it depends on what root is. So for us, it's a little bit still like a black box. We don't know. We're interested because if it's part of this HEP workload in the first place, yes, let's accelerate it. What most likely will happen is similar to what you're saying in your paper, that we will have to design some kind of column-based representation to quickly stream through the data, which is frequently used for a specific task.
Mm-hmm.
Well, I mean, so that maybe gets to the base question is, what kind of what kind of task do you want to tackle, right? The one that the paper about I/O was thinking about analysis, which wants to get to higher and higher processing rates, versus the one that drives cost, arguably. Sorry, the one that arguably drives computing cost, and setting aside personnel cost, is CPU intensive, and you're talking maybe megabyte a second per core, and no, not megabyte a second core, probably less than that, 100 kilobytes a second per core, for the CPU intensive pieces. So there's a bit of a dichotomy there, at least how I see it. Right, so I mean, things like if you're doing something that currently takes 100 seconds per event, thinking too hard about the intermediate or the I/O format, particularly the I/O format that goes to cold storage, is probably not worth it. Versus if you want to go to the use case where you want to do gigabytes a second if possible, then it's really relevant, of course.
Right.
Well, I guess you guys are the users, so I think you tell us what's more important. I mean, theoretically, we can pursue both in parallel, but that's just a lot more load on our side. So it's unclear how much we can handle. So if we have to choose one, either one is fine by us, I think. But what is more important? Maybe you can decide and tell us.
It would probably be pretty obvious whether the file format is a bottleneck based on what problem we choose. So if it's the tracking problem, what we need to do, we need to read hits out of the file very quickly.
But and the way to probably start talking about, ask you what is the most computationally intensive problem, or what is your the most painful bottleneck, or will be a bottleneck when you increase the amount of data by 10 and then again by 10, as you say.
Yeah, if it's tracking, it's the track seeding.
Okay.
Yeah.
So yes, we should concentrate on that.
Yeah, I think that's a good idea. I mean, you mentioned when we were talking about the analysis, you said, oh, well, maybe we should have a look at the code. And of course, the problem with analysis is there isn't the code. There are hundreds or even thousands of codes which are out there all doing slightly different things. And it's not clear to us, although it's an interesting question, could they all be decomposed into some common set of primitives? not at all clear. And in addition, taking into account what we were talking about in terms of this analysis of the problem and then the hours that it takes to program the FPGA to actually do that, that would seem to be much more suitable for areas of our problem space where we want to keep the code extremely stable, but we have very challenging data throughput rates. So actually even more than the reconstruction, let's say, for Atlas and CMS, where already the data has been reduced by 3-4 orders of magnitude, you might even want to consider the tracking problem online, where you have data coming in at 100 kilohertz and you need to reduce it down to a kilohertz. So you have to make a sort of 99-to-1 throwing away of the data. So you have a lot of data coming in, you have very little time, you need to make a fast decision and decide whether this event is interesting or not. And that is definitely the time challenging and stability critical part of our software workflow. So I think maybe tracking in the trigger, that would be a good place to look initially.
Okay. Yeah, I have to say I had included the analysis problem in part because I wasn't, from what you wrote, I hadn't, I was trying to find things that didn't necessarily only deal with the computationally intensive parts, but also the sort of data storage access parts, right? But I think it probably makes sense to focus on one problem rather than several. And Graham is probably right. The most interesting one, in part because we can offer codes, which are maybe already some of these optimized for parallel architectures, right, and a bit cleaner than some of the existing codes, is probably the best one, the best fit to get started.
Sounds good.
Yeah.
Well, analysis, I think, becomes a problem for you guys when the data sets grow. And it just, from what you're saying, is that it looks like the data sets are still smallish, and that's why it's not a problem, right?
No, the problem is that the analysis is too multifaceted.
You will have to wait for hours to complete the analysis. You will be willing to invest time into programming more generic functions, I guess, right? But it doesn't take hours yet, right?
It take weeks.
Yeah, it does. So, but it's probably true that it's sort of a messier. If the focus is more on the computational piece, right, then it's probably a messier problem to approach. There are issues there. I mean, one of the reasons precisely we're focused on what you saw in that paper and some of the other things we've been doing is really to speed that up enough that, as Jim was saying, that the time can be reduced to something that's more interactive. The way it happens now, in the way that happens now, it's actually done in a multi-step process because it takes so long. So people will sort of take a really big data set and then reduce it down by some big factor, right? And then reduce that a second time which leads to all these sort of intermediate data sets around that people are using to try and get to be able to iterate on smaller subsamples, let's say.
Okay.
But I think it's probably true that the tracking and maybe in a sort of trigger environment is then the obvious natural fit to with the focus on the FPGAs. So the next, go ahead.
It's not that analysis isn't a problem. It's just that this solution that you have seems to fit better as something where the code is fixed, well understood.
All right. We may have to wait for the FPGA a bit more, so it doesn't take that long.
But actually, for these small functions, if it was partial reconfiguration, maybe it does take.
Yeah, it takes a lot less, but we would have to experiment. Plus, we would need to identify all the primitives that happen. If we can.
Yeah.
Anyway, I think this may be the next project.
Right. No, I agree. No, and I gave you like the largest possible extent which this project can kind of reach, but we can downsize. We have to be realistic, and especially for NSF to fund us. But one question: so these Monte Carlo simulations are not in scope because they are less interesting for whatever reason.
Monte Carlo simulation sounds like a useful and important problem with fixed, well-defined codes.
Yeah, we could go for that one too. I think the interesting thing is to get. So you mentioned NSF, but there's sort of two parts here, right? There's one sort of getting a concrete working example of something, right, on the table, and that might benefit from just focusing on one or the other, right?
Right.
And then there's if you're going to make a proposal perhaps in the near term, then there's spelling out more than one case, right?
Right. Yeah.
So maybe we should discuss which it is of these things that we're trying to do in the very near future. Because I think for sure we can start some ball rolling on a specific example, but presumably that will play out over some months, right? I don't know if it's something that can be done, in the next month. Were you aiming for that something else on that time scale? For the CSI, for example?
Well, as I'm not quite sure what you're asking, but if we want to try some example before we submit a proposal, just to say that here is some preliminary results, let's call them, then we only have 3 weeks, I guess, for that.
Right.
If we try something just as a way of starting this collaboration, then something that takes a few months is also fine.
So why don't we do it like this? Let's follow up afterwards, so we can put you to some specific code examples, potentially illustrating the tracking problems.
Okay.
Yeah, that sounds good. And also maybe a paper which explains how much data is involved.
Right, we can dig out some example numbers, I think. Okay.
So yeah, go ahead, Peter. Sorry.
No, go ahead. I have to stop something here.
You mentioned the second problem, which was triggering or something, which I probably.
So that's basically just a particular context in which we could be doing. So this tracking problem, we do it basically in a context where we don't necessarily, let's say it's a pseudo real-time context as part of the data reduction coming out of the detector, right? And we don't necessarily need to do the problem in its most complete form, let's say. And then we use that as part of a selection of the data that we keep. And for the data that we keep, we do a much more complete version of the same thing, right? So it's sort of a pseudo real-time, high throughput environment, right? Where we want to do a more basic set of calculations on very large amounts of data. That's the trigger environment. It's a pseudo real-time filter, let's say.
Okay.
And it's also a natural environment where potentially we could have more sort of specialized things like this, right? Because it's sort of less dynamic than the offline environment, where things may evolve a bit more for the complete calculations. But it still boils down to the same, conceptually the same kind of problem, let's say.
Okay.
Okay, so we can follow up afterwards about finding a way to get you some examples, specific examples. Did anyone else have thoughts or questions or ideas on the presentation? Everybody's kind of quiet. Okay, yeah, no, we're almost an hour in. So why don't we do that? Thanks, guys, and we'll follow up.
Thank you so much. We appreciate your time.
Guys, I have just one more sort of unrelated question. I saw a talk here at UCI where a physicist was using machine learning to filter out some events in his experiments. Is that something you guys also do?
It's something that's certainly being explored. So that, for example, the common filter based tracking problem has under it's not just the fitting. You mentioned the sort of fitting of trajectories. It's also a combinatorical problem to put together the things to fit, right? Which has a sort of nonlinear behavior to it. So there are also projects looking to understand how to do these things with machine learning, whether there's ways to sort of reduce the combinatorical aspects of the problem. So the short answer is yes, in various environments. Depends if, which of the experiments you're looking at, what precisely we're trying to do. But.
Okay. Well, I guess this could be yet another possible avenue for collaboration in the future.
Right.
On that line, there's a project called HLS4ML.
HLS. Okay.
People are actually it's a group of physicists who are synthesizing HLS for FPGAs that are based on the output of machine learning algorithms. So you run the machine learning algorithm to identify interesting and not interesting events, and then put that engine into an FPGA. So that is the sort of thing that's already happening.
Okay. HLS4ML. I will have to.
Yeah, we'll take a look.
Look it up.
It's number 4.
Okay.